Every science fiction empire gets it wrong. Every galactic civilization sprawling across the stars in movies and novels violates the same laws of physics that no intelligence, no matter how advanced, can override. The Milky Way contains up to 400 billion stars spread across 100,000 light-years of space. Colonizing even the nearest one would require energy budgets exceeding everything humanity has produced in its entire history. Scaling that effort to a second star doubles the problem. A 10th star does not multiply it by 10, it multiplies it by thousands. The galaxy is not just large, it is a physics engine designed to prevent coherent control. Distance, time, energy, and entropy conspire together to guarantee one outcome: isolation always wins. If you enjoy having your assumptions about the future of civilization completely dismantled by the cold hard math of the universe, do me a favor and hit that like button and subscribe. It genuinely helps this channel keep bringing you these explorations into the science that shapes everything. Now, make yourself comfortable. Let's begin. The Milky Way is not what you think it is. When most people picture our galaxy, they imagine a neat spiral drawn on a classroom poster. A flat disk of stars arranged in elegant arms curving outward from a bright center. That image is useful for introductory astronomy courses. It is catastrophically misleading for understanding why no civilization could ever spread across this structure. The real Milky Way is a three-dimensional monster of almost incomprehensible proportions. It spans approximately 100,000 light-years from edge to edge across its visible disk. That disk measures roughly 2,000 light-years thick in the outer spiral arm regions and swells to nearly 12,000 light-years near the dense central bulge. But the galaxy does not end where the visible stars thin out. An enormous halo of dark matter, ancient globular clusters, and scattered relic stellar populations extends far beyond the bright disk in every direction. Recent measurements place the full extent of the galactic halo at over 200,000 light-years in diameter. Some estimates push even further. This is not a flat shape you can cross by drawing a straight line from one side to the other. It is a vast, three-dimensional volume of space filled with structure, mass, gravitational complexity, and above all else, terrifying emptiness between the points of light. Start with the numbers that matter most. The Milky Way contains somewhere between 100 billion and 400 billion stars. That range itself reveals something important. We cannot even count the stars in our own galaxy with confidence. The uncertainty spans a factor of 4. Thick dust clouds strewn across the galactic plane block visible light from reaching our telescopes across the full breadth of the disk. Entire stellar populations hide behind curtains of molecular gas and interstellar debris that are opaque to optical instruments. Infrared surveys and radio telescope mapping campaigns have revealed enormous numbers of stars in regions that visible light surveys completely missed. The galaxy is so large and so structurally complex that simply cataloguing its stellar population remains an active and incomplete project after more than a century of modern observational astronomy. Yet even the conservative lower bound of 100 billion stars creates a number that overwhelms human cognition. If you counted one star per second without ever stopping to eat, sleep, or pause for breath, you would need more than 3,100 years to finish the count. That is longer than the entire span of time separating the present day from ancient Egypt. If you instead needed to count the upper estimate of 400 billion stars at that same pace, you would need roughly 12,700 years. Longer than recorded human civilization has existed, and each one of those hundreds of billions of stars occupies its own region of space, separated from its nearest stellar neighbours by distances measured not in miles or kilometres, but in light years. Here is where the true scale of the arena begins to bite. The average distance between neighbouring stars in the solar neighbourhood, the relatively well-mapped region surrounding our own sun, is approximately 4 to 5 light-years. One single light-year equals roughly 5.88 trillion miles. So the typical gap separating one star from the next in our local region of the galaxy stretches to at least 24 trillion miles. This is not the empty space between adjacent cities on a highway. This is not the ocean separating two continents that ships can cross in weeks. This is a void so vast and so barren that nothing humanity has ever constructed could traverse it within a single human lifetime, using any technology currently available or plausibly foreseeable. The Voyager 1 spacecraft, currently the most distant human-made object from Earth, has been travelling outward through space for more than 4.5 decades. In all that time, it has covered roughly 15 billion miles. That sounds impressive until you measure it against the interstellar gap. At Voyager's current velocity, reaching the nearest star system, Alpha Centauri, sitting just 4.24 light-years away, would take over 70,000 years. And Alpha Centauri is our closest stellar neighbour. It is the shortest possible crossing in our entire galactic neighbourhood. Every other destination is farther. Most destinations are dramatically farther. But the solar neighbourhood is relatively crowded compared to large stretches of the galactic average. The Sun happens to sit within the Orion Spur, a minor spiral arm structure nestled between the larger Perseus and Sagittarius arms. In this region, stars cluster with moderate density. Move toward the outer edges of the galactic disk, where stellar populations thin out considerably, and the gaps between neighbouring stars can stretch to 10, 15, 20 or even 30 light-years. Move away from the disk entirely into the galactic halo, and individual ancient stars float in near-perfect isolation, separated from one another by hundreds of light-years of functionally empty vacuum. The galaxy is not a uniform field of stars sprinkled evenly like seeds across a garden bed. It is a landscape defined by extreme density variation. The central bulge, a massive spheroidal concentration of older stars surrounding the galactic core, packs stellar populations so tightly that the night sky viewed from a hypothetical planet there would blaze with thousands of individually visible suns. Meanwhile, the outermost spiral arms scatter stars so thinly that a civilization living on the galactic fringe might gaze upon fewer nearby stellar neighbours than we count from Earth. Any serious plan to spread across this galaxy must contend with this density gradient at every stage. Expansion does not proceed through a smooth, uniform medium like a drop of ink spreading evenly through still water. It must navigate alternating regions of relative stellar plenty and vast stretches of stellar nothing, adapting its strategy to local conditions that vary by factors of hundreds or thousands depending on position within the galactic structure. Now consider what this means in terms of raw volume. The Milky Way is not a line to be crossed. It is a space to be filled. If you model just the visible disk as a simple cylinder, 100,000 light-years in diameter and 2,000 light-years thick, the enclosed volume works out to approximately 15.7 trillion cubic light-years. But that cylinder is a dramatic simplification. The real disk is warped along its outer edges. It flares vertically in the outskirts. The central bulge adds substantial volume both above and below the galactic midplane. The stellar halo extends spherically well beyond the disk's edge in every direction. A more physically realistic estimate of the total galactic volume, including the halo regions where globular clusters and relic stars orbit, reaches comfortably into the trillions of cubic light-years. Filling this volume with any kind of infrastructure, communication relays, colony habitats, energy collectors, monitoring probes, or supply depots requires confronting a spatial scaling challenge that does not behave the way most people intuitively expect. Double the radius of your expansion sphere, and you do not merely double the volume you must service, you increase it by a factor of 8. Triple your expansion radius, and the volume grows 27-fold. Expand your reach 10-fold, and the volume explodes by a factor of 1,000. This is the cubic scaling problem inherent to three-dimensional space, and it haunts every model of galactic expansion ever proposed. The galaxy does not merely grow harder to cross as you push outward, it grows harder to fill, harder to monitor, harder to supply, harder to connect. Every additional light year of radius adds disproportionately more volume, more stars, more gaps, and more logistical burden than the light year before it. This brings us to a critical distinction that most popular discussions of galactic civilization completely ignore, collapse, or conflate. There are three fundamentally different categories of activity that people mean when they talk about spreading across the galaxy. Treating them as interchangeable is one of the most common and most destructive errors in thinking about the future of intelligent life in the cosmos. The first category is exploration, sending a probe, a robotic craft, a laser signal, or even a crewed flyby mission to another star system. Exploration is the simplest form of interstellar activity. It requires reaching a destination, gathering data, and potentially transmitting that data back to the origin. It does not require staying at the destination. It does not require building permanent infrastructure. It does not require sustaining a living population at the target star. Exploration is essentially a one-directional energy expenditure, with no obligation for long-term maintenance. Humanity has already performed versions of this within our own solar system. The Voyager missions, the New Horizons flyby of Pluto, and various Mars landers and rovers all represent exploration at interplanetary scales. Scaling this to interstellar distances is extraordinarily difficult, but represents the most plausibly achievable category. A sufficiently advanced civilization could conceivably send robotic probes to nearby stars within decades or centuries of flight time, depending on the propulsion technology employed. The essential qualifier is nearby. Dispatching a probe to Alpha Centauri at 4.24 light-years is a fundamentally different challenge than sending one to a star 40,000 light-years away on the opposite side of the galactic core hidden behind massive dust clouds and intense radiation fields. The second category is settlement, establishing a self-sustaining colony at another star system that can survive independently without ongoing support from the homeworld. Settlement requires everything that exploration requires, plus the capacity to transport a genetically viable population, comprehensive life support systems, construction equipment, or the means to fabricate it from local resources upon arrival, agricultural infrastructure or equivalent food production technology, independent energy generation systems, medical facilities, educational institutions, governance structures, and enough stored knowledge to rebuild critical technologies from scratch if any component fails. Settlement is not a mission. It is the creation of an entirely new self-sufficient civilization from nothing in an environment that provides none of the geological, biological, or industrial support systems the colonists depended upon at home. Every single resource must either be carried from the point of origin at staggering mass and energy cost, or extracted from whatever raw materials the destination system happens to provide. If the destination star system lacks suitable rocky planets with accessible water, if it lacks mineable asteroid belts with useful mineral compositions, if it lacks sufficient energy flux at habitable distances, the colony fails regardless of how technologically sophisticated the colonists may be. Settlement multiplies the complexity of exploration by orders of magnitude. It is the difference between sailing a boat to an uninhabited island and building a fully functional, self-perpetuating nation on that island, with no supply ships ever returning. The third category is empire, maintaining coordinated control, communication, resource exchange, governance, economic integration, or cultural coherence across multiple star systems simultaneously. This is what science fiction invariably portrays when it depicts galactic federations, interstellar republics, trading leagues, or galaxy-spanning imperial dominions. Empire requires everything that settlement requires at every single node in the network, plus the ability to exchange information, resources, personnel, and governing authority between nodes on timescales fast enough to allow coordinated collective decision-making. It requires that the civilization at Star System A can meaningfully observe, respond to, and influence events at Star System B before those events become strategically or logistically irrelevant. It demands shared technological standards, compatible communication protocols, synchronized supply logistics, dispute resolution mechanisms, and a connective infrastructure linking every active node to every other active node in the network. Empire is not merely a larger version of settlement. It is a categorically different class of problem. Settlement asks whether you can survive at another star. Empire asks whether 1,000 independent settlements spread across 10,000 light-years of space can function and persist as a single coherent entity. The answer to the first question might conceivably be yes, given sufficient technology and resources. The answer to the second is where physics itself steps in and says no. Most popular discussions skip directly to empire without acknowledging these distinctions. They assume, often implicitly, that reaching one star leads naturally to reaching the next, which leads to the next after that, which eventually cascades into full galactic colonization as if it were an inevitable chain reaction. This assumption contains a hidden error so fundamental that the entire optimistic argument collapses the moment you identify it. The error is the assumption that expansion scales linearly, that each additional star system added to your growing network costs roughly the same in energy, time, and resources as the one before it. In physical reality, expansion costs scale geometrically and then exponentially, because the volume of space your network must service grows with the cube of your expansion radius, while the coordination infrastructure required to maintain coherence across that volume grows even faster than the volume itself. Reaching Alpha Centauri at 4.24 light-years involves crossing a single interstellar gap between two neighboring stars in one of the denser parts of the local galactic environment. The energy, time, and resources required for this one crossing are enormous, but potentially within reach for a civilization substantially more advanced than our own. Now consider what happens when you attempt to expand outward from Alpha Centauri to additional neighboring systems. The next nearest stars, Barnard's star, at approximately 6 light-years from the Sun, Wolf 359, at roughly 7.9 light-years, Lalande 21,185, at about 8.3 light-years, all sit at comparable distances. Each crossing to each new system demands a separate voyage with its own propulsion energy budget, its own fleet of vessels, its own colonization payload, its own decades or centuries of transit time. Reaching 10 nearby star systems might require 10 independent expeditions, each nearly as expensive as the first crossing to Alpha Centauri. But this cozy local neighborhood represents the easiest possible expansion scenario imaginable. Stars within 20 light-years of the Sun are relatively close together by galactic standards. Push outward beyond this local bubble, and the terrain changes dramatically. Try to expand along the length of a spiral arm, and you must cross not just individual gaps between stellar neighbors, but navigate through inter-arm void regions where stellar density drops by significant factors. Try to push inward toward the galactic center, and you encounter zones of intense radiation, extreme gravitational tidal forces, and stellar densities so high that orbital instabilities make long-term habitation far more complex. Try to cross laterally from one spiral arm to another, and you must traverse thousands of light-years of comparatively empty interarm space, where stars are scarce and staging points for resupply simply do not exist. The galaxy is not a smooth, uniform highway stretching conveniently from departure point to destination. It is a rugged and wildly variable landscape of obstacles, voids, radiation hazards, and density extremes that renders every expansion route uniquely difficult and every additional light-year of reach harder than the last. Let us quantify what galactic empire actually demands in concrete terms. Suppose a civilization aims to establish a coordinated presence along just one major spiral arm. The Perseus arm, which is the nearest major arm outside our own position in the Orion Spur, stretches approximately 30,000 light-years in length. It contains billions of individual star systems. A network covering even a modest corridor of this arm, say outposts positioned at regular intervals within a band, 1,000 light-years wide and 30,000 light-years long, would encompass a spatial volume of roughly 23 billion cubic light-years. The total number of star systems falling within that corridor likely exceeds several hundred million. Every single outpost requires energy generation, communication links to neighboring nodes, supply infrastructure to maintain itself, and sufficient autonomy to survive the centuries or millennia of silence between meaningful contact with the rest of the network. And this is just one arm. The Milky Way possesses 4 major spiral arms: Scutum Centaurus, Sagittarius, Perseus, and the outer arm, plus several minor spurs, branches, and bridge structures. Covering the entire galactic disk would require replicating this kind of infrastructure across every arm, every interarm void, the massive central bulge, and the sparse outer regions. The total number of star systems that would need incorporation into a truly galactic civilization reaches comfortably into the hundreds of billions. The logistical requirements do not merely add up as you expand, they compound and multiply. Each new region incorporated into the network creates new communication pathways that must be actively maintained, new supply chains that must be reliably established across interstellar distances, and new populations that must be sustained in environments that may differ radically from anything the founding civilization ever encountered. The operational complexity does not grow at the same rate as the territory. It grows substantially faster. This is the scalability thesis that drives everything that follows. The core argument of this episode is not that interstellar travel is impossible. It may very well prove achievable for civilizations significantly more advanced than humanity. The argument is that scaling interstellar travel from a single crossing to 100 crossings to 1,000,000 crossings introduces compounding physical constraints that no amount of technological ingenuity can eliminate, because they are not engineering limitations. They are features of the universe itself. You cannot engineer around the speed of light. You cannot manufacture enough energy to fuel 1,000,000 simultaneous colonization missions. You cannot maintain meaningful coordination across a network so vast that a signal dispatched from one edge does not arrive at the opposite edge for 100,000 years. These are not problems awaiting cleverer solutions. They are hard physical boundaries imposed by the geometry of space, the finite speed of information, and the thermodynamic cost of maintaining order across astronomical distances. One final dimension of this arena demands attention before we move forward: time. The Milky Way is not a static target waiting patiently to be colonized. It rotates. The Sun takes approximately 230 million years to complete a single orbit around the galactic center. Stars at different radial distances from the core orbit, at different angular velocities. This differential rotation means that the spatial relationships between star systems are not fixed. They change continuously. A star sitting 30 light-years from your colony today will occupy a completely different position relative to you after a few million years of galactic rotation. The carefully surveyed map that your civilization drew at the start of its expansion program becomes increasingly inaccurate with every passing epoch. Routes that were optimal at launch become suboptimal or even impassable as the underlying stellar geography shifts beneath you. This rotational shearing creates a compounding navigational problem for any long-duration expansion effort. A chain of outposts strung along a spiral arm will experience gradual distortion over time as stars on the inner edge of the chain orbit the galactic center faster than stars on the outer edge. Over millions of years, and galactic expansion necessarily requires operations spanning millions of years, this shearing stretches, warps, and ultimately disrupts fixed network geometries. Maintaining stable routes between colonies demands constant correction and adaptation to account for stellar drift. And the corrections themselves require information about where stars have moved, information that travels at light speed across gaps measured in light years, arriving with inherent delays baked into the physics. You are not building infrastructure on solid, stable ground. You are laying foundations on a slowly rotating platform where every point moves at a different velocity. This is the arena. 100,000 light-years across, hundreds of billions of stars, trillions of cubic light-years of volume, density variations spanning orders of magnitude, interstellar gaps measured in trillions of miles, a structure that rotates differentially, shearing any fixed network on timescales shorter than the expansion itself would require, and three categorically distinct challenges: exploration, settlement, and empire, each exponentially harder than the last, with only the hardest one qualifying as true galactic civilization. Perhaps the sheer scale alone is not sufficient to settle the question. Maybe a sufficiently determined and patient civilization could simply accept the vastness, accept the time requirements, accept the volume, and push through by sheer persistence and brute force engineering. What comes next dismantles that hope by confronting the hardest wall in physics. The speed of light is not a speed limit waiting to be broken by a better engine. It is a structural feature of spacetime itself that dictates exactly how much energy every journey costs, exactly how much time every crossing consumes, and exactly why relativistic travel creates temporal paradoxes that shatter civilizational continuity across interstellar distances. Nothing in the universe moves faster than light. This is not a technological limitation awaiting a breakthrough. It is not an engineering barrier that a sufficiently advanced civilization could overcome with better materials, cleverer designs, or more funding. The speed of light, 299,792 kilometers per second, or approximately 186,000 miles per second, is a structural property of spacetime itself. It emerges directly from the fundamental equations of special relativity, which have been confirmed by more than a century of rigorous experimental verification to extraordinary levels of precision. Every particle accelerator ever constructed, every satellite navigation system ever calibrated, every atomic clock ever synchronized, aboard aircraft and spacecraft confirms the identical result. The speed of light represents the absolute ceiling on how fast information, matter, or energy can propagate through the vacuum of space. No known physics provides a mechanism to exceed it. No speculative physics consistent with observed experimental reality offers a credible workaround. This single constraint, more than any other factor in the cosmos, determines why galactic expansion collapses under the weight of its own ambition before it even begins. Begin with what this speed limit means for travel times across the galactic arena we have already measured. The Milky Way's visible disk stretches approximately 100,000 light-years from edge to edge. At the speed of light itself, the absolute fastest that anything in the universe can travel, crossing the full diameter of the galaxy requires 100,000 years. That number alone should give serious pause to anyone entertaining visions of galactic empires. Light, the fastest phenomenon permitted by the laws of physics, needs a span of time equal to roughly 500 generations of human civilization merely to traverse our single, ordinary, mid-sized spiral galaxy. But no physical spacecraft constructed from matter can travel at the speed of light. The equations of special relativity demonstrate with mathematical certainty that accelerating any object possessing mass to light speed would require infinite energy. Not merely enormous energy, not impractically large energy that might be achieved with better technology, mathematically infinite energy, an amount that cannot be generated by any process in any finite universe. The speed of light is not a wall you can eventually punch through with sufficient force. It is an asymptote that the fundamental structure of reality prevents any massive object from ever reaching. So realistic interstellar travel must occur at some fraction of light speed. The question becomes what fraction is achievable, and what the resulting journey times look like when applied to galactic distances. This is where optimism begins its slow, irreversible collapse. At 10% of the speed of light, a velocity of roughly 30,000 kilometers per second, or approximately 67 million miles per hour, crossing the full 100,000 light-year diameter of the galaxy would require 1 million years of travel time. To anchor that number in something meaningful, consider that 1 million years ago the species Homo sapiens had not yet appeared on Earth. Our predecessor species, Homo erectus, was still the dominant hominin on the planet. Modern language, art, tool-making, agriculture, civilization, none of it existed. A civilization that launched a galactic crossing mission at 10% of light speed would need to sustain that mission continuously for a duration exceeding the entire evolutionary history of anatomically modern humans. And 10% of light speed is an extraordinarily ambitious target. No human technology comes anywhere close to achieving it. The fastest spacecraft ever launched by human hands, the Parker Solar Probe, reached speeds of approximately 635,000 kilometers per hour during its closest approach to the Sun. 10% of light speed is roughly 108 million kilometers per hour. That is more than 170 times faster than the fastest object humanity has ever built. The gap between current capability and 10% of light speed is not incremental. It is a chasm spanning multiple orders of magnitude. At 1% of the speed of light, roughly 3,000 kilometers per second, the galactic crossing stretches to 10 million years. This velocity is closer to what some genuinely proposed interstellar propulsion concepts might theoretically achieve under optimistic assumptions, though even this remains far beyond any current or near-future engineering capability. 10 million years ago, the evolutionary lineage that would eventually produce modern humans had not yet diverged from the lineage leading to modern chimpanzees. The entire arc of hominin evolution, from the earliest bipedal apes through every species of Australopithecus, every variant of Homo, every Ice Age migration, every civilization that has ever risen and fallen on Earth, fits comfortably within the transit time of a single galactic crossing at 1% of light speed. At 1/10 of light speed, 300 kilometers per second, a velocity roughly comparable to the fastest performance achievable by advanced ion drives or theoretical nuclear pulse propulsion concepts like Project Orion, the crossing time inflates to 100 million years. When such a hypothetical mission launched, the dinosaurs would have already been extinct for 35 million years, but the mammals that replaced them would not yet have diversified into most of their modern forms. The entire Cenozoic era, the age of mammals, the epoch that produced elephants, whales, primates, and eventually humans, fits inside this single transit window. These numbers do not merely challenge models of galactic expansion, they annihilate them. Any model that relies on physically transporting ships, crews, or colonization infrastructure across the full breadth of the galaxy requires timescales that exceed the lifespan of any known biological species by enormous margins. They exceed the duration of any known civilizational structure by even larger margins. And they almost certainly exceed the functional lifetime of any technological system that must maintain operational integrity against cumulative radiation damage, micrometeorite bombardment, material fatigue, lubricant degradation, electronic component failure, and the slow but relentless accumulation of entropy over millions of years of continuous operation in the harsh vacuum of interstellar space. This point deserves closer examination because it is routinely glossed over in optimistic models of interstellar travel. The assumption is that if you solve propulsion, you solve the journey. But propulsion only determines whether the ship can move. Survivability determines whether anything functional arrives at the destination. Interstellar space is not a benign medium. It is a relentless degradation environment that attacks every component of every spacecraft through multiple simultaneous mechanisms operating continuously over the entire duration of the voyage. Cosmic radiation represents the most pervasive threat. High-energy particles, primarily protons and helium nuclei stripped from stellar atmospheres and accelerated to near-light speeds by supernova shockwaves and magnetic field interactions, permeate interstellar space at a flux density of roughly 2 to 4 particles per square centimeter per second. Each individual particle carries enough energy to penetrate centimeters of metal shielding and displace atoms within crystalline material structures. Over decades, this bombardment causes cumulative lattice damage in metals, embrittlement in polymers, degradation of semiconductor junctions in electronic systems, and gradual erosion of optical surfaces. Radiation hardening techniques can extend component lifetimes by factors of 10 or perhaps 100, but no known material is immune to cumulative radiation damage over timescales of centuries or millennia. Electronic systems are particularly vulnerable. A single high-energy cosmic ray striking a microprocessor can cause bit flips, logic errors, or permanent transistor damage. Over centuries of continuous exposure, even heavily shielded computing systems accumulate sufficient damage to degrade reliability below functional thresholds. Micrometeorite erosion operates on a different timescale, but with equally corrosive effect. Interstellar space contains a sparse but non-zero population of dust grains ranging from submicrometer particles to fragments several millimeters across. At interstellar cruise velocities, even a modest 1% of light speed, which is 3,000 kilometers per second, the kinetic energy of impact, with even a milligram dust grain, equals roughly 1 kilogram of TNT equivalent. Over centuries of transit through the interstellar medium, the cumulative effect of countless microscopic impacts erodes external surfaces, pits thermal shielding, degrades reflective coatings, and gradually compromises hull integrity. A spacecraft that launched with pristine external surfaces arrives at its destination, scarred, pitted, and structurally weakened by millions of individual micro-impacts accumulated over the journey duration. Material fatigue compounds these external threats with internal degradation. Metals subjected to continuous thermal cycling, as spacecraft surfaces rotate between solar-facing and space-facing orientations, or as internal systems generate and dissipate heat, develop microscopic fractures that propagate over time. Seals and gaskets made from elastomers lose flexibility and develop cracks as polymer chains break down under radiation exposure and thermal stress. Lubricants in mechanical systems evaporate, decompose, or polymerize into useless residues over centuries, causing bearing surfaces to wear and mechanisms to seize. Adhesives degrade, welds develop stress fractures, composite materials delaminate as the bond between reinforcing fibers and matrix materials weakens under sustained environmental assault. The critical question is whether a spacecraft can carry sufficient spare parts and repair capability to counteract these degradation processes over voyage durations measured in centuries or millennia. The answer is almost certainly no for any journey beyond a few hundred years. Carrying replacement components for every system that might fail over a 1,000-year voyage would require a spare parts inventory approaching the mass of the original spacecraft, effectively doubling the mission mass and therefore doubling the propulsion energy required. Carrying manufacturing equipment capable of fabricating replacement parts from raw materials adds further mass and introduces its own reliability challenges, since the manufacturing equipment is itself subject to the same degradation processes afflicting everything else on board. The ship must carry machines to repair the machines that repair the ship, and those machines must themselves be maintained by yet another layer of backup systems, creating a regression of maintenance infrastructure that quickly becomes absurdly mass-intensive. The engineering reality is that every spacecraft has a maximum functional lifespan determined by the slowest degrading critical component that cannot be replaced or repaired en route. For current human technology, this lifespan is measured in decades. Even the most optimistic projections for advanced materials and self-repairing systems might extend functional lifespans to a few centuries. Beyond that, the cumulative statistical probability of cascading system failures, where one degraded component's failure overloads adjacent systems, triggering a chain reaction of breakdowns, approaches certainty. A ship that launches toward a star 10,000 light-years away at 1% of light speed faces a million-year journey. No engineering architecture yet conceived or theoretically plausible could maintain spacecraft functionality across such a duration. The ship would arrive as a dead hulk, a monument to ambition, drifting silently past its intended destination with no functioning systems, no living crew, and no operational capability. Interstellar space does not merely impose time penalties on travel. It actively destroys the vehicles attempting to cross it, on timescales far shorter than the crossing itself requires for all but the nearest stellar destinations. But perhaps relativistic time dilation offers an escape hatch. Special relativity predicts that time passes more slowly for objects moving at speeds approaching the speed of light relative to a stationary observer. This effect is real, experimentally confirmed to extraordinary precision using particle accelerators and orbiting atomic clocks, and mathematically exact. For a spacecraft travelling at 90% of light speed, time on board the vessel passes at roughly 44% of the rate experienced by stationary observers who remained behind. At 99% of light speed, onboard time slows to approximately 14% of the external rate. At 99.9%, it compresses to about 4.5%. This means that a crew aboard a sufficiently fast ship could subjectively experience a galactic crossing in a fraction of the elapsed time measured by external observers. At 99.9% of light speed, a journey spanning 100,000 light-years would feel like approximately 4,500 years to the crew on board, while 100,000 years pass for everyone and everything outside the ship. This sounds like a partial solution until you examine what it actually means for the civilization that built and launched the mission. Time dilation helps the travelers. It does absolutely nothing for the homeworld. While the crew experiences 4,500 years of subjective time, the civilization that designed, funded, constructed, and launched their vessel endures 100,000 years of real, external, uncompressed historical time. 100,000 years of political evolution, cultural transformation, technological revolution, linguistic drift, religious change, ecological disruption, biological adaptation, and social reorganization. When the colony ship finally arrives at its destination on the far side of the galaxy, and its passengers step out into an alien star system, the civilization that sent them has not merely changed. It has been replaced dozens or hundreds of times over by successor societies as different from the original as modern humans are from Neanderthals. The language the colonists speak is incomprehensible to anyone alive at the origin. The cultural values they carry are archaeological curiosities. The technology they brought, which represented the cutting edge of their era, is now 100,000 years obsolete. The colony and the homeworld do not merely find themselves distant from each other. They are separated by a temporal abyss so profound that they share no meaningful cultural, linguistic, technological, or possibly even biological connection. They are strangers in every dimension that matters for coordinated civilization. This temporal severing is not a minor logistical inconvenience that better planning could mitigate. It is a fundamental structural barrier to any form of coordinated galactic civilization. Even if you could send colony ships to distant regions of the galaxy at near light speeds, every colony would arrive in a future that bears no relationship to the past that launched it. There can be no coordination between network nodes separated by tens of thousands of years of independent, divergent evolution. There can be no shared governance across a network where directives issued from a central authority arrive at their destination after the authority itself has risen, transformed beyond recognition, and collapsed into historical memory multiple times over. Time dilation does not solve the expansion problem. It deepens the fragmentation problem by physically guaranteeing that every sufficiently distant colony becomes a fully independent civilization, culturally, technologically, and biologically, from the moment its ship enters cruise velocity. The connection to the origin is severed not by choice but by physics. Now confront the energy costs directly. Even if a civilization accepted the crushing time penalties and the inevitable civilizational fragmentation that relativistic travel imposes, could it physically generate enough energy to accelerate spacecraft to the velocities interstellar travel demands? The calculations are devastating. The kinetic energy of a moving object scales with the square of its velocity at non-relativistic speeds. At relativistic speeds, the relationship becomes dramatically more punishing due to the Lorentz factor, which causes the effective inertial mass of the object to increase asymptotically as it approaches light speed. This means each incremental increase in velocity costs disproportionately more energy than the previous increment. Accelerating from rest to 10% of light speed is enormously expensive. Accelerating from 10% to 20% costs substantially more. Accelerating from 90% to 91% costs vastly more energy than the entire acceleration phase from 0 to 50%. The energy curve is not linear. It is not even simply quadratic at relativistic velocities. It climbs toward infinity as speed approaches the light barrier. Consider a modest interstellar spacecraft with a dry mass, the mass of the vessel excluding fuel, of 1,000 metric tons. This is approximately the mass of the International Space Station, a structure that required decades of multinational cooperation and hundreds of billions of dollars to assemble in low Earth orbit just 400 kilometers above the planet's surface. Accelerating this spacecraft to 10% of the speed of light requires approximately 4.5 times 10 to the 20th joules of kinetic energy. For reference, the total annual energy consumption of all human civilization on Earth, every power plant, every vehicle, every industrial process, every light bulb, amounts to roughly 5.8 times 10 to the 20th joules per year. So accelerating a single ISS mass spacecraft to just 10% of light speed demands approximately 78% of humanity's entire annual energy production. Nearly the full energy output of every power plant, every vehicle, every industrial process on the planet for an entire year consumed by a single ship on a single one-way trip. And that calculation covers only the acceleration phase. The ship must also decelerate at the destination, which requires roughly the same energy expenditure again. And the fuel for deceleration must be carried on board from the start, adding mass to the vehicle, which increases the energy required for the initial acceleration, which demands more fuel, which adds more mass. This vicious cycle is the tyranny of the rocket equation, and it is absolutely merciless at interstellar velocities. The rocket equation dictates that for any spacecraft carrying its own propellant, the ratio of total initial mass, including fuel to final dry mass, increases exponentially with the desired velocity change. For conventional chemical rockets, reaching even a small fraction of 1% of light speed requires fuel masses that would exceed the mass of the Earth. Chemical propulsion is categorically irrelevant for interstellar travel at any meaningful velocity. More advanced propulsion concepts perform better, but still confront crushing constraints when you examine the actual numbers. Fusion propulsion, frequently cited as the most promising near-term interstellar technology, could theoretically achieve exhaust velocities of 3 to 5% of light speed, depending on the specific fusion reaction cycle employed and the efficiency of the magnetic confinement and nozzle systems. A deuterium-helium-3 fusion drive pushing a 1,000 metric ton payload to 10% of light speed and then decelerating at the destination would require a fuel mass of approximately 30 to 50,000 metric tons, depending on engine efficiency assumptions. This represents a fuel-to-payload ratio of 30 to 50. Assembling this quantity of fusion fuel would require mining and processing thousands of metric tons of isotopes from gas giant atmospheres, lunar regolith, or asteroid resources, then transporting, storing, and integrating this fuel with the spacecraft structure in deep space. The industrial infrastructure required to support a single such mission dwarfs any construction project in human history by orders of magnitude. And this entire colossal effort delivers exactly one ship to exactly one star. Antimatter propulsion offers the highest theoretical energy density of any known reaction. The annihilation of matter with antimatter converts approximately 100% of rest mass into usable energy, compared to roughly 1% for nuclear fission and less than 0.5% for the best chemical reactions. But antimatter carries a devastating practical limitation that collapses its promise. Antimatter does not exist naturally in usable quantities anywhere in the known universe. Every single microgram must be artificially manufactured using particle accelerators, and the production process is staggeringly, almost comically inefficient. Current technology at facilities like CERN produces antimatter at an energy efficiency of roughly 1 part in 10 billion. This means that generating 1 gram of antimatter requires approximately 10 billion times more energy input than the energy that gram would release upon annihilation. Even hypothetical far-future antimatter factories, operating at efficiencies millions of times better than current capability, would still consume more energy in production than the resulting antimatter could ever deliver as propellant. Antimatter propulsion does not solve the energy crisis of interstellar travel. It relocates the crisis upstream to the fuel manufacturing stage and dramatically amplifies it. Light sails represent a fundamentally different architectural approach. Instead of carrying fuel on board, a light sail spacecraft is pushed by radiation pressure from a powerful laser array located at the point of departure. The spacecraft carries no engine and no propellant. All propulsive energy comes from the external laser. This elegantly eliminates the rocket equation tyranny because the fuel mass stays behind at the origin. The Breakthrough Starshot initiative has proposed using this concept to send gram-scale probes to Alpha Centauri at approximately 20% of light speed, arriving in roughly 20 years of flight time. The laser array required to achieve this would need to produce approximately 100 gigawatts of coherent, precisely focused power, sustained for roughly 10 minutes per launch. 100 gigawatts is comparable to the total installed electrical generating capacity of a mid-sized industrialized nation, firing simultaneously through a single directed beam. Now scale this concept from a gram-scale wafer probe to a colony vessel massing thousands of metric tons. The required beam power scales linearly with spacecraft mass. Pushing a 1,000 metric ton vessel to 20% of light speed using a laser sail would demand a beam power output on the order of 100 million terawatts sustained throughout an extended acceleration phase, lasting weeks or months. This figure exceeds the Sun's total radiant output discussed earlier by a substantial margin. Launching a single colony ship using light sail technology at galactic relevant velocities would require a laser installation more luminous than our star, and the beam must remain precisely focused on the receding sail across distances that quickly grow to billions and then trillions of kilometers during the acceleration phase, requiring pointing accuracy and optical coherence that make current state-of-the-art systems look like Stone Age tools. Every propulsion method available within known physics confronts the same underlying reality. Interstellar travel at velocities relevant to galactic expansion requires energy budgets that range from civilization straining for single nearby missions to physically impossible when scaled across thousands of destinations. And these calculations apply to individual voyages. A civilization attempting galactic expansion needs not one ship but thousands, then tens of thousands. Each mission targets a different star system. Each carries enough mass to establish a viable colony or functional outpost. Each requires its own full propulsion energy budget, its own fuel supply chain, its own manufacturing and assembly infrastructure. If a single mission to a single nearby star costs energy equivalent to a significant fraction of one star's annual output, then 1,000 simultaneous missions to 1,000 different stars demand 1,000 times that figure. 10,000 missions across a spiral arm require 10,000 times that. A galactic expansion campaign targeting even 1% of the Milky Way's star systems would require cumulative energy expenditures exceeding the total luminous output of the entire galaxy, sustained continuously over millions of years. A common rebuttal proposes that advanced civilizations could harvest energy from multiple stars, perhaps constructing megastructures like Dyson swarms that capture a large fraction of a star's total luminosity. This is theoretically conceivable, but creates a devastating bootstrapping paradox. Building a Dyson swarm around even one star requires disassembling and reprocessing entire planets' worth of raw material, an engineering project that would take centuries to millennia under even wildly optimistic assumptions about self-replicating robotic manufacturing. A civilization that needs Dyson swarms around multiple stars to fund its expansion must first reach those stars to build the swarms, which requires exactly the energy the swarms are intended to generate. You need galactic-scale energy infrastructure to expand across the galaxy, but you need to have already expanded across the galaxy to build galactic-scale energy infrastructure. The logic is circular, and the circle does not close. Even ignoring the bootstrapping paradox, energy collected at one star cannot be efficiently transmitted to where it is needed across interstellar distances. Laser or microwave beams suffer from unavoidable diffraction-limited divergence. Over separations measured in light years, even tightly collimated beams spread to widths measured in astronomical units, reducing received energy density to negligible fractions of what was transmitted. Physically transporting energy via fuel carriers or batteries requires ships, which consume a substantial portion of the energy they carry just to accelerate and decelerate. Energy does not flow across interstellar vacuum the way electricity flows through a continental power grid. It dissipates, degrades, and loses thermodynamic utility with every light year of distance. Each star system is, for practical energy purposes, a self-contained unit that can utilize what it generates locally but cannot meaningfully export surplus energy to distant nodes. One final dimension of the propulsion problem demands attention: the gap between building a single interstellar prototype and manufacturing an interstellar fleet at the scale galactic expansion requires. Solving the physics of one interstellar vessel is a landmark achievement. It requires advanced propulsion, materials science capable of withstanding decades or centuries of deep space exposure to cosmic radiation and micrometeorite flux, radiation shielding adequate for biological or sensitive electronic payloads, autonomous navigation systems accurate across light-year baselines, and power management systems that maintain full functionality over mission durations exceeding any engineering project ever attempted. But one ship is a prototype. Galactic expansion demands mass production at an unprecedented scale. Thousands of interstellar-rated vessels, tens of thousands, each fueled, each loaded with colonization infrastructure, each launched on a unique trajectory toward a different destination star. The industrial base required to manufacture this fleet is not a single factory complex. It is an entire civilizational economy, reorganized around a single purpose sustained across centuries of continuous production. The raw materials required: structural alloys, radiation shielding composites, fusion fuel stocks, electronic components, biological supplies for crewed missions, would demand mining operations across multiple planetary bodies maintained for generations. Quality control standards for spacecraft that must operate autonomously for decades or centuries without any possibility of maintenance, repair, or resupply would need to exceed anything any manufacturing process has ever achieved by orders of magnitude. And every vessel launched permanently depletes the home system's finite resources. Metals fashioned into hull plating and sent to the stars do not return. Fusion fuel burned in transit is gone forever. Electronic components, biological stocks, structural materials, all of it represents an irreversible one-way export of processed resources from the origin system into the interstellar void. A civilization that launches 10,000 interstellar colony missions has permanently exported a significant fraction of its accessible material wealth. At some threshold, the home system exhausts its reachable reserves of critical materials. The expansion program literally consumes the industrial foundation it depends on. This generates a self-limiting dynamic that no technology can circumvent. Early expansion phases target the nearest stars, requiring the least energy and shortest transit times, drawing from a fresh and fully stocked resource base. But each successive wave targets more distant stars, demands more energy per mission, requires longer transit durations, and draws from a resource pool that has been partially depleted by every preceding wave. The marginal cost of expansion rises with every additional star system claimed. Initial colonies might be physically achievable, a second shell of colonies farther out becomes substantially harder, a third shell harder still. Long before the expansion wavefront reaches even a small fraction of the galaxy's full extent, the compounding costs of distance and the diminishing returns of resource depletion grind the program to a halt. Expansion does not radiate outward in a smooth, unstoppable wave. It decelerates, it falters, it stalls. And it stalls not because of insufficient ambition or inadequate engineering, but because the physics of energy, mass, and distance impose hard limits that no amount of cleverness can override. The speed of light sets an absolute ceiling on velocity. Relativistic time dilation guarantees that fast travel severs the temporal continuity between colony and homeworld, ensuring civilizational fragmentation as a physical inevitability rather than a cultural risk. Energy requirements for interstellar propulsion at galactic-relevant velocities scale to levels that strain stellar energy budgets for individual missions and become flatly unachievable when multiplied across the thousands or millions of simultaneous missions galactic expansion demands. Fuel production and fleet manufacturing consume finite, non-renewable material resources that cannot be replenished from interstellar distances. And every propulsion concept available within known physics, fusion drives, antimatter engines, light sails, or any hybrid architecture combining them, confronts the same fundamental thermodynamic limits when scaled from a single proof-of-concept crossing to a sustained galactic colonization campaign. But suppose a civilization absorbed all of this. Suppose it accepted slow expansion measured in millions of years. Suppose it tolerated civilizational fragmentation as an unavoidable cost of spreading outward. Suppose it marshaled colossal energy and accepted the depletion of home system resources as the price of reaching new stars. Suppose it simply sent colonies outward in a gradual wave, each colony becoming an independent entity the instant it departed, with no expectation of maintaining political unity or cultural coherence across the growing network. Even this minimalist, bare-bones model of galactic diffusion, not empire, not coordinated civilization, just independent colonies spreading outward like spores, encounters a barrier more fundamental than distance or energy. The colonies must still communicate. They must receive navigational data to avoid redundantly targeting identical star systems. They must share critical technological discoveries to prevent wasteful parallel development. They must warn each other of stellar hazards, resource shortages, or environmental dangers encountered at destination systems. They must coordinate, at least minimally, to prevent territorial conflict, as expansion fronts from different origin colonies converge on the same regions. Even the loosest conceivable network of fully independent colonies requires some baseline flow of information between nodes, and information, like everything else in this universe, travels at the speed of light. Across galactic distances, this means that messages arrive years, decades, centuries, millennia, or tens of millennia after they were sent, depending on the separation between sender and receiver. What follows examines what happens when a civilization attempts to coordinate any activity at all, across a network where every signal arrives not as current intelligence, but as ancient history. The barrier that kills galactic civilization is no longer motion. It is the absolute, inescapable silence that the universe imposes on every intelligence that dares to spread beyond its own small neighborhood of the galaxy. Information obeys the same speed limit as matter. This fact, which sounds like a minor footnote to the propulsion barriers discussed previously, is actually the single most destructive constraint facing any model of galactic civilization. Ships can theoretically be slow. They can crawl between stars over millennia and still eventually arrive. But information, commands, warnings, trade agreements, navigational updates, diplomatic negotiations, emergency calls, cultural transmissions, scientific discoveries, must travel at the speed of light or slower. There is no known mechanism, no theoretical framework consistent with observed physics, that permits information to propagate faster than 299,792 kilometers per second through the vacuum of space. Every radio signal, every laser pulse, every modulated gravitational wave, every conceivable method of encoding and transmitting a message across interstellar distances is bound by this absolute ceiling. And at galactic scales, this ceiling transforms every act of coordination into an exercise in communicating with ghosts. Begin with the raw delay numbers. A signal sent from Earth to Alpha Centauri, the nearest star system at 4.24 light-years, arrives in 4 years and roughly 3 months. A reply takes an equal duration to return. The minimum round-trip communication time between these closest stellar neighbours is approximately 8.5 years. This means that a question asked today will not receive an answer until the mid-2030s. Decisions requiring back-and-forth negotiation, resource allocation, conflict resolution, trade terms, joint planning, unfold across timescales measured in decades, even between the two closest possible nodes in any interstellar network. For comparison, the average duration of a human government administration is 4 to 8 years. A single round-trip exchange with Alpha Centauri spans 1 to 2 full political cycles. By the time an answer arrives, the government that asked the question may no longer exist. Now, extend the distance. A signal sent to a star system 50 light-years away takes 50 years to arrive. The round-trip delay stretches to a full century. The person who sent the message will likely be dead before the response returns. The institution that composed the message may have been restructured, defunded, or replaced. The political context that motivated the question may be entirely irrelevant. At 100 light-years, a tiny fraction of the galactic diameter, the round trip spans 2 centuries. At 500 light-years, the round trip takes a millennium. The civilization that receives the reply inhabits a world that has experienced 1,000 years of unshared history since the original message was dispatched. Languages evolve beyond mutual intelligibility within 500 to 1,000 years under conditions of separation. The English of the 11th century is functionally a foreign language to modern English speakers. A civilization receiving a reply after 1,000 years of isolation would need archaeolinguists to decode the returning message. At 1,000 light-years, a round-trip communication takes 2 millennia. At 10,000 light-years, the round trip stretches to 20,000 years. 20,000 years ago, the last ice age was still gripping the northern hemisphere. Humans had not yet invented agriculture. The entire arc of settled civilization, Sumer, Egypt, Greece, Rome, the Renaissance, the Industrial Revolution, the Space Age, fits within a single round-trip signal exchange across 10,000 light-years. At 26,000 light-years, the approximate distance from our solar system to the galactic center, a message sent today would arrive around the year 28,000. Any reply would return around the year 54,000. The civilization exchanging those messages would share nothing in common across that 52,000-year gulf, except perhaps basic biology. And even that might diverge given sufficient time and divergent evolutionary pressures. At the full galactic diameter of 100,000 light-years, a single one-way message takes 100,000 years. A round-trip exchange requires 200,000 years. Anatomically, modern humans have existed for approximately 300,000 years. A single round-trip communication across the galaxy consumes 2/3 of the entire existence of our species. Any entity attempting to govern, coordinate, or even loosely monitor a galaxy-spanning network faces feedback loops, measured not in days or months, but in geological epochs. The information arriving from the far side of the galaxy describes conditions that existed before the rise of every human civilization that has ever lived. It is not stale intelligence, it is paleontological data. These delays do not merely slow down coordination, they make coordination mathematically impossible beyond a certain network radius. To understand why, consider what coordination actually requires. At its most basic level, coordination means that 2 or more nodes in a network make decisions informed by knowledge of each other's current state. A supply chain works because the factory knows how much inventory the warehouse currently holds. A military command structure works because headquarters knows where its units are currently positioned. An economy works because buyers and sellers have approximately current information about prices, availability, and demand. Remove the word current from any of these systems, and they collapse into chaos. In an interstellar network, no node ever possesses current information about any other node. Every piece of data arriving from another star system describes conditions as they existed years, decades, centuries, or millennia ago, depending on distance. A colony 100 light-years away that reports a critical shortage of rare earth elements is describing a crisis that began a century ago. By the time the message reaches the coordinating authority, the colony has either solved the problem independently, adapted its technology to work without those elements, collapsed entirely, or evolved its society in directions the coordinating authority cannot predict. Any response dispatched from the authority will take another century to arrive, delivering a solution to a problem that has been resolved, transformed, or forgotten for 200 years. The response is not helpful. It is an archaeological curiosity arriving from a distant past that no longer has any bearing on the colony's present reality. This is not a failure of bandwidth or signal strength. Increasing the data rate does not help. Sending 1,000,000 bits per second instead of 1,000 bits per second still delivers information that is 100 years out of date. The problem is latency, not throughput. And latency is fixed by the speed of light and the distance between nodes. No technology can reduce it. No relay system can accelerate it. No compression algorithm can compensate for the fact that the information describes a reality that no longer exists by the time it arrives. Now consider what happens as the network grows. A civilization spanning 10 star systems within a radius of roughly 20 light-years faces communication delays of up to 40 years for round-trip exchanges between the most distant nodes. This is difficult but arguably manageable for a long-lived civilization with stable institutions. Decisions can be made on generational timescales. Cultural coherence can be maintained through regular exchanges of media, scientific publications, and diplomatic correspondence, even if each exchange takes decades. The network is small enough that the lag, while painful, does not fundamentally break the ability to function as a loosely connected entity. Expand the network to 100 star systems, spanning perhaps 200 light-years. Round-trip delays between the most distant nodes now reach 400 years. No government structure in recorded human history has survived 400 years without radical transformation. The Roman Republic lasted roughly 5 centuries before becoming the Roman Empire, which itself fragmented and fell within another 5 centuries. The civilization at one edge of this 100-system network cannot meaningfully govern, trade with, or culturally synchronize with the civilization at the other edge, because 4 centuries of independent development separate every exchange. Different nodes begin developing divergent technologies, divergent social structures, divergent languages, and divergent priorities. The network does not merely stretch, it begins to fracture along lines defined by communication delay. Expand further to 1,000 star systems across 2,000 light-years. Round-trip delays between extremes hit 4,000 years. This exceeds the entire lifespan of every empire in human history combined. The nodes at opposite ends of this network are not members of the same civilization in any meaningful sense. They cannot coordinate economic activity because price signals arrive millennia too late to be actionable. They cannot coordinate defense because threat warnings arrive after the threat has either been resolved or has conquered the warned system millennia ago. They cannot share scientific knowledge effectively because discoveries transmitted from one end arrive at the other after the receiving civilization has independently developed equivalent or superior knowledge through its own 4,000-year research program. The network is not a civilization. It is a constellation of independent civilizations that happen to share distant ancestry, communicating through messages that carry the informational value of ancient scrolls discovered in archaeological digs. This escalating breakdown follows a precise mathematical pattern that can be described as coordination decay. As the number of nodes in a network increases, the number of unique pairwise communication channels grows proportionally to the square of the node count. 10 nodes require 45 unique channels. 100 nodes require 4,950 channels. 1,000 nodes require nearly 500,000 channels. 10,000 nodes require approximately 50 million channels. Each channel carries its own latency penalty, determined by the distance between the two nodes it connects. Managing this network means processing information from millions of channels, each delivering data with a different time lag, each describing conditions at a different historical moment, each requiring interpretation in the context of a reality that has evolved independently since the data was transmitted. The computational challenge of maintaining coherence across such a network is not simply large, it is fundamentally intractable. The information required to make an optimal coordinating decision for the network as a whole includes the current state of every node. But the current state of every node is unknowable because it can only be inferred from data that is years or centuries out of date. Any decision based on this stale data is a decision made in partial ignorance. As the network expands and delays increase, the fraction of relevant information that is actually current shrinks towards zero. Eventually, the coordinating authority is making decisions based almost entirely on historical data that bears no relationship to present conditions at any node. At that point, central coordination is not merely inefficient, it is actively harmful because decisions optimized for conditions that existed centuries ago will be wrong for conditions that exist now. The nodes are better off making independent decisions based on local information than following directives issued by a distant authority operating on ancient data. This is not speculation about alien psychology or political philosophy. It is an information theoretic constraint that applies to any network of any kind, biological, electronic, social, or political, where the latency of communication between nodes exceeds the timescale on which conditions at those nodes change. When the lag exceeds the rate of change, coordination becomes impossible regardless of the intelligence, goodwill, or computational power of the coordinating entity. The galaxy imposes communication lags measured in millennia. Civilizations change on timescales measured in centuries or less. The mismatch is fatal to every model of coordinated galactic governance. Resource coordination faces an even more specific version of this collapse. A galactic civilization is not merely exchanging abstract messages. It must allocate physical resources, energy, raw materials, manufactured goods, biological stocks, technological components across its network of star systems. Some systems will be resource-rich, others will be resource-poor. Some will specialize in energy production, others in manufacturing, others in agriculture or biological sciences. Any functional multi-system economy requires that resources flow from where they are abundant to where they are needed, guided by information about supply and demand at each node. But resource shipments between star systems travel at speeds far below light speed. Even the most optimistic propulsion scenarios we have already examined place interstellar transit times for physical cargo at decades to centuries, for nearby stars and millennia, to millions of years for distant ones. A shipment of critical materials dispatched from a mining colony to a manufacturing hub 50 light-years away will take centuries to arrive even at an ambitious fraction of light speed. The manufacturing hub must plan its production schedule around supply shipments that were dispatched generations ago, based on demand forecasts made centuries before the shipment arrives. If demand has shifted during the transit period, which it certainly will have, given that entire technological paradigms can rise and fall within a few centuries, the arriving shipment may contain materials that are no longer needed, in quantities that no longer match requirements, produced to specifications that are no longer compatible with current manufacturing systems. Supply chain management is one of the most complex coordination problems in modern economics, even when communication delays are measured in milliseconds and shipping times in days. Introduce communication delays of years and shipping times of centuries, and the entire framework of supply chain logistics ceases to function. There is no algorithm, no predictive model, no artificial intelligence system that can accurately forecast demand across centuries of independent civilizational development at a distant node. The variables are too numerous, the interactions too complex, the butterfly effects too pervasive. A star system that urgently needs titanium alloys today might need synthetic organic compounds by the time the titanium shipment arrives 3 centuries from now. The sending system has no way to know this because the demand signal will not reach them for another 50 years, by which time the receiving system's needs will have changed again. This logistical paralysis extends to every form of physical exchange. Technology transfer becomes meaningless when the transmitted blueprints describe manufacturing processes that were state-of-the-art at the sending node centuries ago, but are hopelessly obsolete by the time they arrive. Military reinforcements dispatched to assist a threatened colony arrive centuries after the threat has been resolved one way or another. Medical knowledge shared between star systems arrives after the diseases it addresses have either been independently cured or have evolved beyond the treatment's efficacy. Cultural products, literature, music, art, philosophical traditions arrive as historical artifacts from a foreign civilization, rather than as contemporary contributions to a shared culture. The net effect is that each star system in the network becomes functionally self-sufficient, not by choice but by necessity. Relying on imports that take centuries to arrive is not a viable economic strategy. Waiting for instructions from a distant capital that will not arrive for millennia is not a viable governance strategy. Depending on military allies whose reinforcements will show up long after the war has ended is not a viable security strategy. Each node must develop its own complete resource extraction, manufacturing, energy production, scientific research, medical, agricultural, and defensive capabilities independently, because the network cannot deliver any of these things on timescales relevant to the node's actual needs. But a star system that must be entirely self-sufficient in every domain has no functional need for the network. The network provides nothing that local self-sufficiency does not already supply. The connections between nodes become ceremonial, symbolic links to a shared ancestral heritage, rather than functional channels delivering actual value. The civilization has not spread across the galaxy. It has shattered into thousands of independent civilizations that share a common origin but nothing else of practical significance. The impossibility of interstellar resource coordination has a specific economic consequence that deserves explicit examination because it demolishes the foundational premise of every fictional galactic economy ever imagined. Interstellar trade, the exchange of physical goods between star systems for mutual economic benefit, is not merely impractical at galactic scales. It is thermodynamically nonsensical. Trade functions when the cost of transporting a good from producer to consumer is less than the value that good provides to the consumer. On Earth, shipping a container of electronics from Shenzhen to Los Angeles costs a few $1,000s and takes roughly 2 weeks. The electronics inside are worth far more than the shipping cost, so the trade is profitable and therefore sustainable. Now apply this logic to interstellar distances. Shipping physical cargo between star systems requires accelerating that cargo to a significant fraction of light speed, sustaining the voyage across years or decades of transit, and decelerating at the destination. As we have already seen, the energy cost of accelerating even modest masses to interstellar velocities is comparable to the annual energy output of entire civilizations. The energy cost of shipping 1 metric ton of any material to a star system 10 light-years away dwarfs the value of that material by factors of millions or billions, regardless of how rare or precious the material might be. There is no substance in the periodic table, no element, no alloy, no manufactured component whose value per kilogram could justify the energy expenditure required to ship it across interstellar distances. Gold, platinum, enriched uranium, advanced microprocessors. The energy cost of delivery exceeds the utility value of the delivered goods by so many orders of magnitude that the transaction is thermodynamically absurd. You would burn more wealth in fuel than you could ever recover in the value of the cargo delivered. Even information trade, the exchange of scientific data, cultural products, or technological blueprints encoded as electromagnetic signals, faces crippling limitations beyond the latency problems already discussed. Information has economic value only when it arrives in time to be acted upon, and only when the receiving civilization possesses the context and infrastructure to use it. A blueprint for a revolutionary new energy system, transmitted from star system A to star system B, arrives decades or centuries later. During that transit time, star system B has independently developed its own energy technology, optimized for its own local conditions and resources. The arriving blueprint describes a system designed for star system A's specific environment, its available materials, its stellar energy spectrum, its gravitational conditions, its atmospheric chemistry. Adapting the design for star system B's entirely different conditions requires engineering effort equivalent to designing a new system from scratch. The transmitted information provides negligible advantage over independent local development because the contexts have diverged too far for direct technology transfer to function efficiently. Financial systems face an even more fundamental collapse. Money functions as a medium of exchange only when both parties in a transaction share a common monetary framework, a currency, a banking system, a mechanism for enforcing contracts and settling debts. Across interstellar distances with communication delays measured in decades or centuries, no shared financial framework can operate. You cannot extend credit across a 50-year communication lag because the borrower's economic conditions will have transformed beyond recognition before the lender receives even the first status update. You cannot price goods in a common currency because currency values fluctuate based on economic conditions that diverge independently at each star system. You cannot enforce contracts because the legal systems at each node evolve independently, and any enforcement mechanism requires communication and physical presence that the distances involved make impossible. The entire apparatus of finance, banking, insurance, futures markets, investment, debt instruments depends on timely information flow and enforceable agreements between parties. Remove timely information flow and enforceability simultaneously, and financial systems do not merely become inefficient, they become logically incoherent. There is nothing to trade, no way to pay, no mechanism to enforce delivery, and no framework to adjudicate disputes across communication gaps measured in human lifetimes. There is a tempting counter-argument that deserves direct confrontation. Perhaps a galactic civilization would not attempt centralized coordination at all. Perhaps it would adopt a decentralized model, allowing each colony full autonomy while maintaining the network purely for information sharing rather than control. Each node governs itself, makes its own resource decisions, develops its own technology, and simply broadcasts its accumulated knowledge outward for any other node that might find it useful. No central authority, no coordinated resource allocation, no governance hierarchy, just a loose web of independent civilizations sharing information at the speed of light. This model is more robust than centralized coordination, but it still fails at galactic scales. Even passive information sharing requires that the information be useful when it arrives. Scientific data transmitted from one node to another remains valuable only if the receiving node's technological context has not diverged so far that the data is incomprehensible or irrelevant. A breakthrough in quantum computing transmitted to a node that independently abandoned electronic computation 2 centuries ago in favor of biological neural networks provides no value. The two civilizations have diverged down incompatible technological paths. Their knowledge bases no longer overlap sufficiently for transmitted data to be integrated into the receiving civilization's framework. This technological divergence is not hypothetical. It is inevitable given sufficient time and independence. Civilizations facing different environmental challenges, different resource availabilities, different biological makeups, and different cultural priorities will develop different technologies. A colony orbiting a red dwarf star in a resource-poor system will develop entirely different engineering solutions than a colony in a resource-rich system orbiting a sun-like star. Over centuries of independent development, their technological traditions will become as mutually incomprehensible as the engineering principles of medieval European cathedral builders and modern semiconductor fabricators. Both are sophisticated, both solve real problems, but neither can meaningfully contribute to the other's work without extensive translation and context building, that itself takes generations. Language drift compounds the problem catastrophically. Human languages mutate, branch, and diverge on timescales of centuries. After roughly 1,000 years of separation, two populations descended from the same linguistic stock will speak mutually unintelligible languages. After 5,000 years, the languages may share so few common roots that the relationship is undetectable without sophisticated comparative analysis. A galactic network where signals take thousands of years to traverse experiences exactly this kind of linguistic fragmentation. Messages arriving from distant nodes are not merely delayed. They are encoded in languages that the receiving civilization no longer speaks, references cultural concepts that the receiving civilization does not share, and uses technical terminology that maps to no equivalent in the receiving civilization's vocabulary. Decoding these messages becomes a task for historians and linguists rather than administrators and engineers. The information channel has not been severed. Photons still arrive carrying modulated signals, but the semantic content of those signals has become inaccessible without scholarly interpretation that itself introduces delays and potential misunderstanding. Even mathematical and scientific notation, often proposed as universal languages immune to cultural drift, cannot fully escape this problem. Mathematical truths are universal, but mathematical notation is not. The way a civilization encodes, transmits, and interprets mathematical relationships depends on its notational conventions, its computational paradigms, its conceptual frameworks, and its educational traditions. Two civilizations that have independently developed advanced mathematics may arrive at equivalent truths expressed in mutually incompatible formalisms. Translating between these formalisms is possible in principle, but requires sustained scholarly effort that consumes time and intellectual resources that could be spent on independent research. The cost of maintaining inter-civilizational communication compatibility eventually exceeds the benefit of the information received, at which point rational nodes simply stop trying to decode incoming signals from distant, divergent sources. The communication barrier also destroys the ability to maintain consistent standards across the network. Technological compatibility requires shared standards, common units of measurement, compatible data formats, interoperable hardware specifications, agreed-upon communication protocols. On Earth, maintaining international standards requires constant committee work, regular updates, and ongoing negotiation between parties that can communicate in real time. Now imagine maintaining technological standards across a network where the standards body publishes an update that takes 500 years to reach the most distant node. By the time the update arrives, the distant node has independently developed 3 generations of incompatible replacement standards optimized for its own local conditions. It has no incentive to adopt the centrally published standard, because doing so would require scrapping centuries of locally optimized infrastructure in favor of a specification designed half a millennium ago for conditions that may never have existed at the distant node's location. Without shared standards, physical interoperability between nodes becomes impossible. A spacecraft designed and built at one star system cannot dock at facilities designed at another system thousands of light years away, because their engineering specifications diverged centuries ago. Fuel produced at one node is incompatible with engines designed at another. Data formats are mutually unreadable. Communication protocols are mutually unintelligible. The network's physical infrastructure fragments into thousands of locally optimized but mutually incompatible subsystems. There is no galactic internet because there is no agreed-upon protocol stack. There is no galactic trade because there are no compatible cargo standards. There is no galactic military because there are no interoperable weapon systems or command structures. Each node is a sealed pocket of locally coherent technology, surrounded by mutual incompatibility, imposed not by hostility or negligence, but by the simple impossibility of maintaining shared standards across communication delays, measured in centuries and millennia. The cumulative effect of all these communication-driven breakdowns can be summarized in a single principle. Coherent coordination requires that the communication latency between nodes be shorter than the timescale on which conditions at those nodes change significantly. When latency exceeds the rate of change, coordination degrades. When latency vastly exceeds the rate of change, as it does at galactic scales, coordination collapses entirely. What remains is not a civilization but an archipelago of independent societies, connected by threads of ancestral memory, growing thinner and more tenuous with every passing century. This principle imposes a maximum coherent radius on any interstellar civilization. The exact radius depends on assumptions about how quickly civilizations change and how much latency coordinated systems can tolerate. If a civilization can tolerate round-trip delays of up to 50 years, roughly one human lifetime, then the maximum coherent radius is approximately 25 light-years. This encompasses perhaps a few dozen star systems. If a civilization with exceptionally stable institutions could tolerate round-trip delays of up to 500 years, the maximum coherent radius extends to roughly 250 light-years. This might include a few thousand star systems. If an immortal, post-biological civilization with perfect institutional continuity could tolerate round-trip delays of 5,000 years, already an extraordinarily generous assumption, the coherent radius reaches approximately 2,500 light-years, encompassing perhaps tens of thousands of star systems. Even the most generous estimate, 2,500 light-years, represents only 2.5% of the galactic diameter. A civilization pushing coherence to its absolute theoretical maximum would still control less than 1,000th of the galaxy's volume, and this maximum assumes perfect institutional stability over millennia, instantaneous internal decision-making, zero technological drift between nodes, and a tolerance for communication delays that no known civilizational structure has ever demonstrated. In practice, the coherent radius is almost certainly far smaller, measured in tens or hundreds of light-years rather than thousands. The galaxy is simply too large, and the speed of light too slow for any coordinating intelligence to maintain meaningful influence across more than a tiny fraction of the galactic disk. This does not mean interstellar civilizations are impossible. Small clusters of nearby star systems could plausibly maintain some degree of coordination, exchanging messages and resources across delays of years or decades. These local clusters would function as independent civilizational units, stellar neighborhoods bound together by manageable communication lags and feasible resource exchange timescales. But the clusters themselves would be isolated from one another by gaps that impose communication delays beyond any coordinating system's tolerance. The galaxy would not host one civilization. It would host thousands or millions of small, independent, mutually isolated civilizational clusters separated by communication barriers as impenetrable as any physical wall. But communication collapse, devastating as it is, still leaves one final line of defense for proponents of galactic expansion. Perhaps individual colonies need not coordinate at all. Perhaps each colony simply survives independently, reproducing the expansion process from its own local position, sending out daughter colonies that send out their own daughter colonies in an ever-expanding wave of autonomous settlement, requiring no communication, no coordination, no shared standards, and no central authority. Just biology, doing what biology does, reproducing and spreading outward. Even this minimalist model, stripped of every coordinating function, faces a final and inescapable physical barrier. Every colony, every outpost, every autonomous settlement must fight a war it can never win permanently. The war against entropy. Every structure degrades, every energy source depletes, every isolated system trends toward disorder over time. Maintaining a colony against the relentless pull of thermodynamic decay requires constant energy input, constant material renewal, constant active resistance against the universe's most fundamental tendency. Scaling this fight across thousands of independent colonies, separated by light years of empty vacuum, sustained over millions of years of galactic time, introduces constraints that make even the communication barrier look forgiving. But there remains one final enemy deeper than all the others, not distance, not speed, not silence, but the thermodynamic reality that the universe is an entropy machine, and every structure built within it is temporary. The second law of thermodynamics is the most democratically enforced law in all of physics. It does not care how intelligent you are. It does not care how advanced your technology has become. It does not care whether you are a single-celled organism clinging to a hydrothermal vent or a post-biological superintelligence commanding the energy output of an entire star. The second law states that the total entropy of any isolated system, its measure of disorder, randomness, and thermodynamic uselessness, must increase over time. Energy degrades from concentrated useful forms into dispersed, unusable waste heat. Ordered structures decay into disordered rubble. Complex arrangements of matter trend relentlessly towards simpler, more probable configurations. This is not a tendency that can be reversed by clever engineering. It is the statistical consequence of how energy and matter behave at the most fundamental level of physical reality. You can fight entropy locally by pumping energy into a system to maintain its order, just as a refrigerator fights the natural tendency of heat to equalize by continuously consuming electricity. But every local victory against entropy comes at a global cost. The energy used to maintain local order generates waste heat that increases entropy elsewhere by an even greater amount. The universe's total entropy always rises. Always. Without exception. And this law, more than distance, more than the speed of light, more than the energy crisis of propulsion, is the deepest reason why galaxy-spanning civilization is physically unstable. Every structure ever built by any civilization requires continuous energy input merely to continue existing. A building must be maintained against weather, corrosion, settling, and material fatigue. A computer must be powered, cooled, and periodically repaired as components degrade. A biological organism must eat, breathe, and repair cellular damage every moment of its life. Stop the energy input and the structure decays. This is not a flaw in design. It is the fundamental thermodynamic cost of maintaining any ordered system in a universe that trends toward disorder. The more complex the structure, the more energy it requires to resist entropic degradation. A mud hut requires minimal maintenance. A skyscraper requires enormous ongoing investment in structural repair, climate control, elevator maintenance, plumbing, and electrical systems. A space station requires constant monitoring and replacement of seals, filters, radiation shielding, atmospheric recyclers, and thermal management systems. An interstellar colony, a fully self-sustaining habitat operating in the vacuum of space or on the surface of an alien world with no supply lines to any external civilization, represents the most maintenance-intensive structure imaginable. Every component must be locally manufactured, repaired, or replaced from locally available resources. Every failure cascade must be locally contained and corrected. Every energy system must be locally fueled and locally maintained. The thermodynamic cost of keeping a single interstellar colony functional is staggering, even under optimistic assumptions about technology and resource availability. Now multiply this maintenance burden across thousands of colonies spread over thousands of light years. Each colony fights its own independent war against entropy, using only the energy and materials available in its local star system. Some systems will be energy-rich, orbiting bright, stable stars with abundant planetary resources for manufacturing replacement components. These colonies might sustain themselves for millions of years, continuously repairing, upgrading, and replacing degrading infrastructure. Other systems will be energy poor, orbiting dim red dwarfs or sitting in resource-scarce environments where critical raw materials are difficult to extract. These colonies will face a constant thermodynamic deficit, spending more energy on maintenance than their local environment can sustainably provide. Over centuries and millennia, they will fall behind the entropic curve. Systems will fail faster than they can be repaired. Infrastructure will degrade faster than it can be replaced. The colony will simplify, shrink, and eventually collapse, not because of any dramatic catastrophe, but because the slow, grinding arithmetic of entropy eventually overwhelms any finite energy budget. This entropic attrition is not a dramatic event. It does not announce itself with explosions or alarms. It is a gradual statistical process operating on timescales of centuries and millennia. A colony that is thriving in its first 1,000 years might begin showing signs of strain in its second 1,000, as original infrastructure reaches the end of its functional lifespan, and replacement components prove slightly less reliable than the originals due to accumulated manufacturing drift. By the third millennium, critical systems might require workarounds and jury-rigged repairs because the precision manufacturing capabilities needed to produce exact replacements have themselves degraded. By the fifth millennium, the colony's technological capabilities may have regressed measurably from their initial level, not because the colonists became less intelligent, but because the cumulative burden of maintaining complex systems without external inputs inevitably erodes the technological base over sufficiently long timescales. This process is called technological regression, and it has abundant historical precedent even on Earth, where supply lines are short and civilizational neighbours are close. The Roman Empire at its height maintained engineering capabilities, concrete formulations, aqueduct construction, road-building techniques, architectural methods that were lost for centuries after the empire's fall, not because the knowledge was deliberately destroyed, but because the institutional, economic, and logistical infrastructure required to sustain those technologies could not be maintained once the imperial system that supported them fragmented. Medieval Europe could not reproduce Roman concrete for roughly 1,000 years. The technology existed in written records. The knowledge was theoretically available, but the complex industrial supply chains, specialized training programs, and institutional continuity required to actually implement that technology had decayed beyond recovery. Now imagine this regression dynamic operating on an interstellar colony with no external civilization to eventually rediscover what was lost. Every technological capability that degrades is gone permanently unless the colony independently reinvents it from first principles using whatever diminished resources remain available. Stellar timescales add another layer of entropic constraint that operates above and beyond the maintenance burden of individual colonies. Stars are not eternal. They are nuclear furnaces consuming finite fuel supplies on timescales measured in billions of years. Sun-like stars, spectral class G, the type that hosts our own solar system, burn through their hydrogen fuel in approximately 10 billion years. Our Sun is currently roughly halfway through its main sequence lifetime. In approximately 5 billion years, it will exhaust its core hydrogen, swell into a red giant that engulfs the inner planets, and eventually shed its outer layers to leave behind a slowly cooling white dwarf. Any colony orbiting a Sun-like star has a maximum operational window dictated by that star's remaining main sequence lifetime. After that, the colony's primary energy source transforms in ways that render the local habitable zone uninhabitable. Red dwarf stars offer much longer lifetimes. The smallest red dwarfs will burn for trillions of years, far longer than the current age of the universe. A colony orbiting a stable red dwarf theoretically has access to a nearly inexhaustible energy source on any timescale relevant to civilizational survival. But red dwarfs present their own challenges. They are significantly dimmer than Sun-like stars, meaning habitable zone planets must orbit extremely close to their host star. At such close distances, tidal locking becomes likely, creating permanent day and night hemispheres with extreme temperature differentials. Red dwarfs are also prone to intense stellar flares that can strip planetary atmospheres and irradiate surfaces with lethal doses of ultraviolet and X-ray radiation. A colony orbiting a red dwarf gains longevity but pays for it with a harsher, less stable local environment that imposes its own chronic maintenance burdens. More massive stars, spectral classes O, B, and A, burn far hotter and faster, exhausting their fuel in tens or hundreds of millions of years rather than billions. These stars offer enormous energy output but on timescales too short for any slow-expanding civilization to fully exploit. A colony established around a bright B-type star might enjoy tremendous energy abundance but face the star's death within 100 million years, forcing either evacuation to a new system, with all the propulsion and energy costs already established, or extinction. The diversity of stellar lifetimes means that a galactic civilization's network of colonies does not age uniformly. Different nodes in the network face different energy timescales, depending on their host stars. Some colonies lose their primary energy source after a few 100 million years. Others persist for billions. Coordinating a network where different nodes have fundamentally different operational lifespans adds yet another layer of complexity to an already impossible management problem. And over the truly long timescales that galactic expansion requires, tens of millions to billions of years, the stellar population of the galaxy itself changes. New stars form in molecular cloud nurseries. Old stars die in supernova explosions or quietly fade as white dwarfs. The galactic environment is not a static stage on which civilizations can build permanent structures. It is a churning, evolving system where the very energy sources that colonies depend upon are themselves temporary features of the landscape. The galaxy's rotation compounds this temporal instability. The Milky Way, as we have already seen, rotates differentially, with inner regions completing orbits faster than outer regions. A single galactic rotation takes approximately 230 million years. Over the timescales required for galactic expansion, certainly tens of millions of years and more likely hundreds of millions, the galaxy completes significant fractions of a full rotation. Stars that were adjacent at the start of an expansion program will have drifted to entirely different galactic neighborhoods by the time the program reaches its middle phases. Spiral arms, which are density wave patterns rather than fixed material structures, will have propagated through the disk, sweeping some colony systems into denser environments and leaving others stranded in interarm voids. The physical map of the galaxy that any expanding civilization relied upon becomes obsolete on timescales shorter than the expansion itself requires. Building a permanent network across a structure that rearranges itself every few 100 million years is not merely difficult, it is building on foundations that are guaranteed to shift beneath you. Now consider the thermodynamic cost of maintaining network infrastructure, specifically the relay stations, communication beacons, navigational markers, and resource depots that any interstellar network requires between its primary colony nodes. Every piece of infrastructure positioned in interstellar space, away from a host star, lacks access to continuous stellar energy. It must either carry its own power supply, nuclear reactors, radioisotope generators, or stored energy reserves that deplete over time, or receive beamed energy from a distant star system, suffering the same catastrophic transmission losses we have already encountered. Either way, the infrastructure has a finite operational lifetime, determined by its energy reserves or the reliability of its energy supply link. A communication relay stationed midway between two star systems, 50 light-years apart, sits 25 light-years from the nearest energy source. Beaming energy to this relay from either star system suffers the same catastrophic diffraction, divergence losses that plague all interstellar energy transmission. The relay must therefore carry its own onboard power supply. A nuclear fission reactor using uranium fuel might operate for a few decades before requiring refueling. Refueling that requires a physical mission from the nearest colony, taking decades or centuries to arrive depending on propulsion technology. A radioisotope thermoelectric generator using plutonium-238 has a half-life of roughly 87 years, meaning its power output drops by half every 87 years. After a few centuries, the generator produces insufficient power to operate the relay's communication systems. The relay goes dark. The link between the two star systems it served is severed. Replacing or refueling dead relays requires dispatching maintenance missions, ships carrying fuel, replacement parts, or entirely new relay hardware across interstellar distances. Each maintenance mission incurs the same energy and time costs as any other interstellar voyage. A network of thousands of relays spread across thousands of light years would require a continuous pipeline of maintenance missions cycling between colony systems and relay positions, each mission consuming energy and resources that could otherwise be used for colony maintenance or new expansion. The maintenance burden of the network infrastructure alone becomes a significant thermodynamic drain on the civilization's total energy budget. At some network density and extent, the energy required to maintain the network's connective infrastructure exceeds the energy the network's colonies can spare from their own local survival needs. The network becomes a thermodynamic parasite, consuming more resources to maintain its connections than those connections provide in value. At that point, rational nodes will stop investing in network maintenance because the return on investment has gone negative. They will focus their finite energy budgets on local survival, rather than maintaining links to distant systems that provide no actionable benefit. The network does not collapse because of a single catastrophic failure. It withers because the economics of entropy make its maintenance unsustainable at sufficient scale. All of these constraints, colony-level entropic decay, stellar lifetime limitations, galactic rotation, and network infrastructure maintenance costs, converge on a single concept that defines the ultimate physical limit on interstellar civilization: the galactic fragmentation horizon. This is the maximum radius from any central point, any homeworld, any founding colony, any civilizational core, at which a connected, coordinated civilization can maintain physical viability before the combined effects of communication delay, energy transmission losses, entropic maintenance costs, and temporal instability make coherence impossible. The fragmentation horizon is not a single fixed number. It depends on the technological level of the civilization, the efficiency of its energy systems, the stability of its institutions, and its tolerance for communication delay. But even under extraordinarily generous assumptions, the horizon is small relative to the galaxy. A civilization with fusion-level energy technology, highly efficient life support systems, and institutional stability spanning millennia might maintain coherent coordination across a radius of a few hundred light-years. This would encompass perhaps several thousand star systems, a substantial interstellar presence by any measure, but one that occupies a volume representing far less than 1% of the galactic disk. A hypothetical post-biological civilization with near-perfect energy efficiency, effectively immortal institutional memory, and tolerance for communication delays measured in thousands of years might push the horizon to perhaps 1,000 or 2,000 light-years. This would encompass tens of thousands of star systems, impressive but still representing a tiny ember in the vast darkness of an entire galaxy. Beyond the fragmentation horizon, colonies are not lost or destroyed, they simply become independent. They continue to exist, to evolve, to develop their own cultures and technologies and aspirations, but they are no longer part of the founding civilization in any functional sense. They are daughter civilizations, related by ancestry, divergent in practice, and increasingly alien to one another as centuries and millennia of independent development accumulate. The galaxy does not fill with one expanding civilization. It fills, if it fills at all, with thousands or millions of small civilizational clusters, each bounded by its own fragmentation horizon, each operating independently, each separated from its neighbors by gulfs of space and time that no communication or transport system can meaningfully bridge. This is not the dramatic, catastrophic failure that science fiction imagines when galactic empires fall. There are no rebellions, no interstellar wars, no dramatic collapses driven by corruption or tyranny. The fragmentation is quiet, structural, and inevitable. It is imposed not by the failings of any civilization but by the geometry of space, the speed of light, the thermodynamics of energy, and the arrow of time. A civilization that expands beyond its fragmentation horizon does not fail. It succeeds locally and fragments globally. It creates pockets of interstellar achievement surrounded by distances that guarantee those pockets will never cohere into a unified galactic whole. This understanding reframes the question that motivates so many discussions about galactic civilization. The famous Fermi paradox asks why, given the vast number of stars and the enormous age of the galaxy, we see no evidence of galaxy-spanning civilizations. The question assumes that a sufficiently old and advanced civilization would naturally expand to fill the galaxy, making its presence obvious through megastructures, communication signals, or direct physical evidence. The physics examined across this episode suggests a different answer. The galaxy is not empty because civilizations fail, destroy themselves, or never arise. It may be quiet because the physical structure of the universe makes galaxy-spanning coherence impossible. Civilizations may arise frequently. They may achieve interstellar travel. They may establish colonies around nearby stars and build thriving multi-system cultures spanning hundreds of light years. But they do not fill the galaxy, because filling the galaxy requires sustaining coordinated expansion across 100,000 light-years of space and millions of years of time, against the combined resistance of light-speed delay, energy scarcity, entropic decay, and temporal instability. The expansion fragments. The fragments persist as local clusters. The clusters never merge into a galactic whole, because the physics that fragmented them continues to operate at every scale. The Milky Way may be dotted with thousands of small civilizational clusters, each occupying a few hundred or a few thousand light-years of space, each invisible to the others across the vast interstellar gulfs that separate them. From within any one cluster, the galaxy appears empty and silent, not because no other civilizations exist, but because those civilizations are too distant, too isolated, and too divergent for their signals to be detectable, interpretable, or meaningful. The silence is not evidence of absence, it is evidence of distance. The universe does not forbid intelligence. It forbids the coherent propagation of intelligence across scales that exceed the physical limits imposed by thermodynamics, relativity, and the structure of space-time. This conclusion does not declare galactic expansion absolutely impossible. It would be intellectually dishonest to claim that no civilization, under any conceivable circumstances, could ever establish any presence beyond its fragmentation horizon. Slow diffusion of independent colonies, each founding its own local cluster, each cluster eventually spawning its own daughter colonies that found their own clusters, could theoretically seed the galaxy with life over timescales of hundreds of millions of years. But this process would not produce a galaxy-spanning civilization. It would produce a galaxy populated by millions of independent, mutually isolated civilizational islands, each one unaware of most of the others, each one evolving along its own unique trajectory, each one bounded by the same fragmentation horizon that limited its parent culture. The galaxy would be alive but not unified, populated but not connected, full of intelligence but devoid of empire. The universe favors isolation. This is not a punishment imposed on civilizations for some cosmic transgression. It is not a filter designed to test the worthiness of intelligent species. It is a structural property of physical reality as fundamental and as impartial as gravity itself. The speed of light creates communication horizons that shrink effective network size to tiny fractions of the galactic volume. The thermodynamics of entropy impose maintenance costs that drain finite energy budgets and cause technological regression over millennia. The finite lifetimes of stars guarantee that the energy sources colonies depend upon are themselves temporary. The differential rotation of the galaxy rearranges the physical landscape faster than any expanding civilization can map and adapt to it. And the cubic scaling of three-dimensional volume ensures that every increment of expansion radius demands disproportionately more resources, more energy, more coordination capacity, and more maintenance than the increment before it. These are not problems that better technology can solve. They are constraints embedded in the fabric of the universe at the deepest level of physical law. A civilization 1,000,000 years more advanced than humanity would face the same speed of light. It would face the same second law of thermodynamics. It would face the same finite stellar lifetimes and the same cubic volume scaling and the same differential galactic rotation. Its tools would be vastly more sophisticated than ours. Its energy systems would be incomparably more efficient. Its institutional structures might endure for timescales we cannot imagine, but it would still fragment at some horizon. That horizon might be larger than ours, perhaps significantly larger, but it would still be finite, and it would still be vanishingly small compared to the 100,000 light-year diameter of the galaxy it inhabited. The Milky Way is not empty because civilizations destroy themselves in nuclear wars or artificial intelligence catastrophes or ecological collapse. Those scenarios may or may not occur, but they are not necessary to explain galactic silence. The galaxy is quiet because it is too large, too old, and too entropic for any single organizing intelligence to hold together across its full extent. The speed of light ensures that information arrives too late to coordinate action. The energy economics of interstellar travel ensure that expansion decelerates and stalls long before reaching galactic scales. The thermodynamics of entropy ensure that every structure, every colony, every network node fights a losing war against decay that eventually claims everything not continuously sustained by local energy inputs. And the timescales of galactic evolution ensure that the playing field itself transforms faster than any civilization can adapt its network to match. What remains is not a galaxy devoid of life or intelligence. What remains is a galaxy where life and intelligence arise in scattered localities, build outward to the limits physics permits, and then persist as isolated islands in an ocean of space, too vast and too old for any bridge to span permanently. Local civilizations may burn brightly for millions of years. They may achieve wonders we cannot currently conceive: orbital habitats, terraformed worlds, stellar engineering, perhaps even feats of physics we have not yet discovered. But they will achieve those wonders locally, within their fragmentation horizons, within the volumes of space where the speed of light permits coordination, where energy budgets permit maintenance, and where entropy can be held at bay through continuous, sustainable effort. The galaxy does not punish ambition, it simply enforces limits. Those limits are written in the equations of relativity, thermodynamics, and quantum mechanics, the same equations that permit stars to burn, planets to form, and life to emerge in the first place. The physics that creates the possibility of intelligence is the same physics that constrains its spread. The universe gives rise to minds capable of dreaming about galactic empires, then quietly ensures that those empires can never cohere across the distances it provides. This is not tragedy, it is structure. The Milky Way is not a territory to be conquered. It is an archipelago of possibility, where each island of intelligence lights its own small fire against the darkness, visible only to its nearest neighbours, invisible to the rest. The silence between the stars is not empty. It is full of physics, doing exactly what physics has always done, shaping what is possible, and gently but absolutely forbidding what is not. And perhaps there is something unexpectedly beautiful in this conclusion. Humanity has spent centuries dreaming of galactic empires, vast civilizations commanding millions of star systems, their fleets crossing the spiral arms, their authority spanning the disk from core to rim. Those dreams are magnificent. They speak to something deep in the human desire to explore, to grow, to leave a mark on the cosmos that outlasts any individual life. But the universe is offering us a different vision. Not empire, not conquest, not a galaxy brought under a single banner. Instead, a galaxy that blooms with countless independent fires, each one a unique expression of intelligence shaped by the particular conditions of its own small corner of the cosmos, each one solving the puzzle of existence in its own way, each one burning with its own light, asking its own questions, building its own wonders, completely unaware of the thousands of other fires burning in other distant corners of the same vast galaxy. This is not a lesser outcome, it is a richer one. A galaxy ruled by a single civilization would be a galaxy of conformity, one set of values, one technological paradigm, one cultural perspective imposed across 100 billion star systems. A galaxy of isolated clusters is a galaxy of diversity on a scale that defies comprehension. Every cluster, an independent experiment in what intelligence can become. Every pocket of civilization a unique answer to the question of how life organizes itself when given energy, matter, and time. The galaxy is not diminished by the absence of empire. It is enriched by the presence of countless independent minds, each one a sovereign expression of what the universe can produce when physics permits complexity to emerge from chaos. We are one such fire, burning in the Orion spur of a mid-sized spiral galaxy, surrounded by distances we may never cross, silences we may never break, and timescales that dwarf everything we have ever built or imagined. The galaxy will not yield to our ambition. It will not shrink to fit our reach. It will remain vast, ancient, mostly empty, and structurally resistant to the coherent spread of any single intelligence across its full magnificent extent. But here, in our small corner, we burn. We ask questions. We build telescopes and point them at the darkness. We listen for signals we may never receive. And we begin, slowly, to understand the architecture of the universe that made us. An architecture that creates islands of light in an ocean of distance, and trusts each island to illuminate its own small patch of the infinite dark.